Let's start with a number that feels impossible. In 1969, the computer that flew 3 men to the moon had less memory than a single email you might send this morning. This is the story of the Apollo guidance computer, and I want to persuade you it's the most impressive machine ever built, not because of what it had, but because of what it achieved with almost nothing. 4 kilobytes. That's it. That is the entire working memory of the computer that guided Apollo 11 across 380,000 kilometers, landed it on the moon, and brought the crew home. To put that in perspective, this slide alone contains more data. And yet with 4 kilobytes, the AGC ran navigation, rendezvous, and landing calculations in real time. Let me show you how. Here's our roadmap. We'll start with the machine itself, what the AGC was and what it could do. Then the people, especially Margaret Hamilton and the team who wrote its software. Then the moment that proved it all, the moon landing. And finally the legacy, why a 1960s computer still matters to everything you use today. We begin with the machine. Picture a computer about the size of a briefcase, weighing 70 pounds, that NASA strapped into a spacecraft and trusted with human lives. It had to be flawless. There was no cloud, no reboot, no second chance. Let's meet it. The AGC was the brain of the entire mission. It handled guidance, navigation, and control, what engineers call GNC. It collected data from sensors automatically and made the mission-critical calculations for both the command module and the lunar module. This was the first time a computer did this job in real time, embedded inside a spacecraft. The astronauts flew the mission, but the AGC did the math that kept them alive. Look at the raw numbers. A clock speed of 2 megahertz, 4 kilobytes of RAM, and about 72 kilobytes of ROM stored in a thing called core rope memory. 55 watts of power, 70 pounds of weight. These numbers are laughably small today, but they were the cutting edge of 1966. Every one of these numbers had to be exactly right. It was compact, 60 by 30 by 15 centimeters, because every gram cost fuel. The astronauts talked to it through the DSY, a display and keypad console that looks primitive now but was the cockpit interface of its era. Astronauts entered commands and read data through a few glowing digits and a keypad. Imagine navigating to the moon with that. Now the people. The AGC was brilliant hardware, but it was nothing without software, and the software had to be perfect. That responsibility fell to a mathematician named Margaret Hamilton and the team she built. Their work redefined what software could be. Margaret Hamilton led the software engineering division at MIT's Instrumentation Laboratory. She and her team wrote the onboard flight software for both the lunar module and the command module. And here's the astonishing detail. The code wasn't typed and stored on a disk. It was literally sewn. Copper wire threaded through tiny magnetic rings, each wire representing ones and zeros. Software you could hold in your hands. Hamilton did something else remarkable. She made software a discipline. She's credited with popularizing the term software engineering itself, and she meant it. She insisted that code flying humans to the moon had to be as rigorously engineered as the rocket. That mindset, testing, verification, treating software as engineering, is now the foundation of everything from banking to medicine. And that brings us to the legacy. The AGC was the first real-time embedded computer, a computer that reacts to its environment instantly. That idea, born here, now lives in your car's brakes, your phone, your airplane, your router. The landing is the proof, but the legacy is the platform. Here's the arc. Development began in 1962 under Charles Stark Draper at MIT. The machine was introduced in August 1966 and flew that December. In 1969, it carried Apollo 11 to the moon, and the program ran until 1975. In just over a decade, a team went from concept to landing humans on another world, with computing power far weaker than a modern smartwatch. This is the moment. The lunar module Eagle is descending, and the AGC is running the landing in real time, processing radar data, firing thrusters, updating the trajectory second by second. With 4 kilobytes of RAM, it brought 2 men safely to the surface. If that doesn't convince you that constraints can drive brilliance, I don't know what will. So why should you care in 2026? because every device you carry is a descendant of this machine. The AGC pioneered the real-time embedded systems that run your car's safety features, your phone's sensors, your home's smart devices. The discipline Margaret Hamilton created is why software doesn't fail more often than it does. This is not ancient history. It's the foundation you're standing on. Here's the takeaway I want to leave you with. The Apollo guidance computer did the impossible with almost nothing, because its builders were clear, disciplined, and creative under brutal constraint. The lesson isn't about megabytes. It's about what focused teams can achieve when they treat constraints as a design problem. If 4 kilobytes could reach the moon, imagine what your team can do with the abundance you have. The question isn't whether you have enough. It's whether you have the same clarity and nerve.